From an ohmic conductor to a semiconductor, we have seen that resistance can change depending on the material we are using. We have, however, not covered the most common type of resistance behaviour. Resistance changes with temperature. A filament lamp is a very good example of how temperature affects the resistance of materials. We know that resistance is a property of a material, which slows down the flow of electrical charge. But how does it do this? The answer is quite simple. An electron is made to move through a wire by induction. An external agent gives it a signal to move. The level of this movement is measured by the potential difference across the wire, but nevertheless, the electron is made to move. It isn't just one electron that is made to move, but billions of them in the wire. It is like a long conga line, where each electron is connected to the one in front and behind. Each of these billions of electrons is induced to move by a small amount, but the small amounts move in one direction, meaning that a current is formed. What stops these electrons from moving? As the electron is a negative charge, then a positive charge can pull it forward if it is in front of it, in the direction of flow, or it can slow it down if it is behind it. The opposite is true of the other electrons floating around the atoms. The electrons that we have induced to move have many obstacles to overcome on their journey along, mostly provided by the nuclei of the atoms in the material it is moving through. This is bad enough when the nuclei are not moving very much, or the movement of the nuclei is of little effect, as in our examples so far. But when the nuclei are dancing around like a swarm of bees, the job of moving through the material becomes a lot more difficult. Temperature is a direct measure of the average motion of nuclei in a material. The higher the temperature of a material, the more the nuclei are moving around. From our discussion before, it must therefore follow that as temperature increases, resistance increases as well. Furthermore, the current applied to a material causes more electrons to travel through a material and therefore collide with more nuclei and make more of them move around. This increases the temperature of the material. Next time you have left your hairdryer on for a while, hold the cable that has connected it to the plug socket. It should be noticeably warmer than the background temperature. This is also the major source of energy loss in any electricity distribution system, such as the national grid. The cables transmit huge amounts of electricity and therefore heat up quite a lot as well. We see this in the voltage current graph of a filament bulb very clearly. Because the filament is so thin, it heats up a great deal, as the wire has a high intrinsic resistance. As the bulb gets hotter, the resistance of the bulb gets higher. The voltage current graph, with voltage on the y-axis, show a steady ohmic pattern when the voltage is low and the current low, and therefore a low temperature. As you increase the voltage going to the bulb, you increase the current and therefore the temperature. The graph curves upwards as voltage increases and current doesn't as much. If you were to reverse polarities and have the current going backwards, we would see the same pattern repeated. As voltage was increased, the current would decrease, and we would have a graph curved downwards towards the y-axis.